Alright, algebraic limits and continuity. Develop and use limit principles to calculate limits. Determine whether a function is continuous at a point. This first example here, let's go to the next page. Limit properties. If the limit of f of x as x goes to a, and f of x approaches L, and the limit of g of x as x goes to a and approaches M, and c is any constant, you have the following. The limit of any constant is a constant. As x approaches a, the limit of a constant is the constant. The behavior of the output is going to be a constant, no matter what a is. A is. Limit properties here. The limit of f of x to the n is going to be that output value raised to the nth power. And the same thing with square roots. You take the square root. The limit of the square root is the same thing as the square root of the limit. The limit of a sum or difference is the sum of the difference of the limits. F of x plus g of x, the limit of f of that sum is the same thing as the sum of the limits here. The limit of a product is the same thing as the product of the limits. The limit of the product is the same thing as the product of the limits. The limit of a quotient is the quotient of the limits. The limit of a constant times the function is the constant times the limit. So to do this one here, use limit properties to find it. Since we're given this here, limit of x is equal to 4. This is equal to 4 here. I have an x squared here, so limit of x times limit of x times 3 times the limit of x plus 7. So it's equal to 4. So we can plug a 4 in here. Then it simplifies here. 11 is the answer. Alternate approach. Because we know the limit of x approaches 4. We can go ahead and rewrite that here. So you can substitute in, simplify it, and that's our answer there. Limits of rational functions. For any rational function of f with a in the domain of f. Okay, the limit of that function is f of a, whatever that approaches. So here's another one here. Okay. So using that rule there, the limit of f of a. So I put in that a is 0 and substitute. I get 2 here for my answer. So here they ask us to find the limit here. Take the limit of x. We know that it's, in this case, it's 1. We simplify it. Do it again here. The limit of a quotient of the limits. I'm going to take the limit of the numerator and denominator here. 5.1 divided by 10, which is 5.1 for my final answer. Last one here. So here I have the square root, limit, square root of the limits. In this case, it's equal to 2. So I plug in a 2. Simplifies. There you can see it. Another example here. Okay. Now they ask for the limit of 3. Limit of -3 because it's not in the domain. If you simplify it here, we can evaluate that -3. So that's what we do. We factor, cancel. Now we can evaluate that -3. We end up with a -6. So notice here, the limit exists as x approaches 3, but the actual point doesn't, because it's not defined at -3. But the behavior is there, but it's not defined at that point. Number 4. In this case here, we have variables in the numerator and denominator here. It doesn't factor easily. So I divide divide by the highest power of x squared, and it simplifies. That's right there. Now when I take the limit, of a constant, it's going to be that constant. This one here, as x gets larger and larger, it's going to infinity. X gets large, this goes to 0. This gets large when it goes to 0. Limit of a constant is constant. That gets larger, it gets close to 0. So my final answer here is 1/2. This one here, go through the same process, dividing by the highest power of x here. Then we take the limit, we simplify it. See how the x cubes cancel? So that's how we get that right there. Then we take the limit of each term in the numerator and the denominator. Some go to 0 and some will be 1. So when you do that there, when you take the limit of it, as x gets large, it gets close to 0. This way, as x gets large, it gets close to 0. So my final answer is 2/3. Now look at continuity. A function is continuous at a if f of a exists, the limit exists, and the limit is equal to the function value at that point. If it's true, then it's continuous over the interval. And this one here is this one. It's a continuous at 3. So f of 3 is at 4. Take the limit of it. That's 4. Since the limit is equal to the function value at that same point, it's continuous at 3. Look at this one here. It's continuous at -2. So they look at g of -2. They put it in for -2. They have a -3. So it's defined at the point. Look at the limits. So you get, on the left side, you get a 2, and on the right side, you get a 3. The limits don't equal, so it's not continuous at -2. Okay, is this one continuous? Is it defined at the point? G of 2 is 5. So they look at the left-hand side and the right-hand side. They're not equal. So it's not continuous. Is this one continuous? They look at the limit. The limit of the function is 6. So the limit is 6. However, when it's 3, at 3, at the function, h of 3 is 7. So they're not equal. The limits do not equal the function value. So it's not continuous. And there's our summary. For a function, a rational function for which a is in the domain, the limit is x of a. If the direct evaluation leads to an indeterminate form, the limit may still exist. Algebraic simplification or a table graph may be used to find it. Informally, a function is continuous if its graph can be sketched without lifting off the paper.